Machine learning has changed in the area of AI agents, and has changed from what we used to teach primarily in machine learning course, which is induction, to a form of inference that we call transductive. And I'll say what that means in a second. This is a flow chart of my talks, partly occluded by the windows, that will give you a sense of where I am and how long the segment that I'm covering is, so you get a sense of how long before the next stage. So don't be shy. Feel free to interrupt me if I say something that you don't understand. Okay? That's the benefit of being here in Flesh and Bones. Can we sort of remove it? Yeah, you would hope so. Let's see if, okay, this one may be more difficult to remove, but let me try. I can, oh, there you go. Better? All right. Okay, so I will try to walk you through what is the way in which current learning models operate, which is transductively, which stands in contrast with the type of process which you do when you use machine learning techniques for inference, which is called induction. Okay, so I'll start with a cartoon. I'm slightly oversimplifying here how we teach machine learning, but roughly speaking, the idea is the following. So let's say that you're faced with a decision, which is in this case whether to eat this fruit or not. And presumably you want to base that decision on some type of measurement of the chances that you will be alive or dead tomorrow if you eat this fruit. Of course, you don't have a pre-built function that tells you anything related to chance or probability of an event happening in the past condition on some data you observed. So you don't know how to evaluate this criterion. But you have seen other fruits in the past, and you have seen your friends eating them, and some of them are okay, and some of them didn't make it. And so then you could wonder, how do I use this experience on data I will never see again to inform decisions on data I've never seen before? And that's what we teach in classical machine learning, which is the process of induction, from particular to general, from particular data we've observed in the past to a general function that we can use forever after. So how do we get that function? Well, we say, let's pick some type of function that we can think of it as a probability or as a likelihood, and let's make sure that we adjust the parameters of the function so that the likelihood of what we actually observe is maximized with respect to the unknown parameters w, okay? And then once we have this function, we just apply it to data we have never seen before and cross fingers. Right, that's induction, okay? Now, when I say cross fingers, in reality, we teach that there is a theory behind this way of operating, which is generalization theory. And roughly speaking, it says that if you have a data set D drawn from some distribution P, which is unknown, then you can instantiate a function, for instance, the log likelihood of that probability that I showed you before, and optimize it with respect to the parameters, then apply that function on data you never seen before, so long as that function is sampled from the same probability, which you don't need to know, then you're still guaranteed that the error you will make in the future on data D prime that you've never seen before is close to the error you make in the past, which you can make however small you want. That's totally under your control. That's a training loss, so long as you keep your model not too complex. And complexity here is measured by the mutual information between the trained weights and the data set, okay? So these are called uniform generalization bounds, Pak-Bayes bounds. There's a variety of them, okay? That's machine learning 101 in one slide for you, okay? So, and then we say, you don't want to, you can certainly reduce the training loss to 0, right? You can make this term as small as you want, especially with an over-parameterized model. But in order to do that, you will have to memorize the data set in the weight, so we don't like that solution, right? That's called overfitting or memorization. So at the same time, we can minimize the complexity in the weights, for instance, by putting random weights. Of course, then we'll pay a price in the training loss. And in practice, you want to trade off the two, and this is the kind of the concept of Occam's razor. You want among all explanations, meaning the parameters that optimize the data, you want the simplest ones, the ones that retain as little as possible of the data set, right? So that's, in a nutshell, generalization theory. Does it make sense? You recognize yourself? Yeah? All right, let me ask a question again. Does it make sense? Yes. You see anything wrong with this equation, with this bound, or with this story? Okay, this story doesn't make any sense. Okay? Now, this is a known problem. It's not my claim. So this is what Hume said in 1736. Hume was interested in understanding what is the rationale for induction, because induction is what we do. Okay, whatever worked in the past, we apply for the future and cross fingers. So is there a rationale to it? Is there a logic to it? And what you see from this bound is that that unknown distribution P has to be the same in the past and forever after in the future. So Hume reasons that if there is a logic to induction, that logic implies that future data must resemble past data, and the course of nature is stationary, nothing ever changes, which is obviously not true, and therefore there is no logic to induction. Okay? So also, when somebody shows you a bound where the same unknown quantity is present on the left-hand side and the right-hand side, something is fishy, right? So this is a problem with induction. And the issue is that if you are a philosopher, the problem of induction is unsolvable because it always relies on the belief that future data will behave as past data did, which is unverifiable and arguably unfalsifiable and arguably false, right? So you can keep talking about it for hundreds of years. If you are a philosopher, that's good news. In mathematics, we bypass the problem completely. We say data are generated by logical production rules that we decide beforehand, stemming from a set of axioms that we declare true, and that's the world. And everything else we don't consider, okay? Now, in biology, this is what we do. This is called system one behavior, reactive behavior, okay? You have some procedures that worked in the past, you apply them in the future and cross fingers, and the reason we do it is that most of the time it actually works, right? Except that sometimes it doesn't, and when it doesn't, in biology, that's taken care of by evolution. You eat the fruit was poisonous, you die, too bad, your friends will see you, they will not eat the fruit, right? So, but the message here is that the problem of induction is absent in agentic AI, okay? And that is a game changer, okay? So, let me walk you through what is the alternative to induction. So if induction doesn't make any sense, contrary to what all of you believe and what I've been teaching for 27 years, unfortunately, I'm sorry for that. So what does the transductive caveman do? Well, the transductive caveman wants to be able to make a decision on whether to eat this fruit based on information about this fruit, not other fruit, okay? So the transductive caveman can put in place an algorithm, a procedure, a process that will gather information about this fruit. For example, he can convince one of his friends to eat the fruit and then watch if they're alive or dead, right? And if they're dead, okay, I know I will not eat the fruit. If they're alive, well, maybe I feel confident but not so confident, so I'll keep waiting until I'm confident enough. And the issue is that sooner or later, I will be able to make my confidence arbitrarily high. By the time every single fruit of the tree has been eaten, I know, and all my friends are alive and well, I know that it was edible. But of course, by then, it's useless to me. And what if I reach the optimal decision, but in a time by which the fruit has spoiled, so it's of no use to me? So the point is that in transductive inference process is going from particular to particular. So I'm not interested in a function that allows me to determine whether any fruit is edible. I want to know where this fruit is edible, from particular to particular. And there, in an agentic setting, the question is not how to minimize the uncertainty on the outcome of inference, which is the goal of inductive learning. It is how to minimize the time it takes to make a specific decision about this data. Okay, it's a completely different perspective on learning. Okay? So you can always design an algorithm that for any function f that specifies the task and for any datum x will test any hypothesis y with arbitrary confidence. The question is, will you be able to get an answer in time in which the answer is actually useful to you? So Is the difference between inductive and transductive inference clear? So inductive inference is from particular, a specific training set, no matter how big, to general, to an inference function that it will use forever after. Whereas transductive inference is from particular to particular. I want an optimal answer for this particular task. Let me give you a slightly less trivial example, AI code generation. How many of you have used a model to generate code? How many of you have not used AI to generate code in the past week? 1, 2, 3. What is wrong with you guys? Seriously? So you don't write code or you write it by hand? You write it by hand. Okay. Okay. Rough times ahead. So let's say you want a model to generate a piece of code that will write a calculator app or will control a physical actuator, whatever task suits you. So inductive code generation is where a model trained on a particular set of data, however big you want, will generate a piece of code that will have to work forever after, right? So you're familiar with vibe coding. Professional developers prefer spec coding, which is where in vibe coding you give some instruction, then the model inductively generates some code, then you look at the code and says, well, no, then you change the prompt and interact this way, but the model operates in open loop inductively. It's you who close the loop. In spec coding, you write very detailed specification of all the constraints and the things that the model has to specify, typically in English. The process is called prompt and pray or model bagging. And then you let the model generate the code. This is inductive code generation, okay? Now, I have bad news for you because if you generate a piece of code today, at some point tomorrow it will break because there will be libraries that get updated, there will be 5 formats that didn't exist when you wrote the code, so something will break because, as Hume said, nature is not a stationary process, things change. So transductive code generation is where you generate code for a particular input when that input becomes manifest. And next time you get a different input, you may generate a different piece of code or the same piece of code, okay? So I'll walk you through later on what is transductive code generation. But as a preview, we put out an open source library that allows you to write AI-generated code transductively. And I'll explain more in detail what it means, okay? All right, is that a little more clear what is the difference between induction and transduction? Okay, so now, yes? Yes?
Why is that one called like inductive? The spec coding, why is that one called inductive? What is like inductive about it?
Inductive means that you write your prompt, the model generates one piece of code, and that is the piece of code that you will deploy forever after on any input. So your code will have to cover all corner cases, including inputs that may never appear. So it will be a very complex piece of code, very difficult to write, and once you write it, that's it. Okay? Once the world changes, that will die. Transductive is when you write a piece of code for that specific input, not for any input. And then for a different input, you might write a different piece of code. Okay? Okay, so the reason why we're talking about transduction is because large language models are inductively trained transductive inference engines. Okay? And if you understand this word, then that's basically all I'm talking about in this talk. So if you understand that, you're done. I don't expect you to understand it, so I'll spend the rest of this talk trying to go through the details of that. So, but is this shift to transduction, which was not planned, it emerged in a trained model, is that good? Is that a new thing? All right, so certainly it's not new. Here's your picture from 1956 Dartmouth conference that gave name of AI. That's your friend Claude Shannon. And Shannon information theory is an intrinsically inductive concept. You're talking about properties of distributions. But in the same spot was also Solomonoff, and Solomonoff was the champion of algorithmic information theory, and what is now known as Solomonoff induction, which is an unfortunate name because it's actually optimal transductive inference. Okay, so I'll say in a second what that is. Okay, so certainly it's not a new idea. Is it good? Okay, why should we worry about transduction? Well, yes, it is good in theory. In fact, it is so good that you cannot do better, provably. So this is a preview of the next few slides. Okay? In 1964, Solomonoff wrote a paper that answered the following question. In classical inductive learning, you say, I have data from some distribution P, unknown. Okay? How do I design or learn the best function to perform inference on data from the same distribution? Okay? Because I believe that there exists one world, one distribution, one true model generating data that will persist forever, so I want to create algorithms that will allow me to do inference optimally for that distribution. Solomonoff says that distribution doesn't exist. Is there an algorithm which is optimal for any distribution? Doesn't matter what it is, same that I use for training or different, doesn't matter. Is there one algorithm that is good for any universal, for any distribution, okay? So all physically generated data is generated by computable distributions. That's called the Church-Turing hypothesis. So you want algorithms that are optimal with respect to data generated by any computable distribution, any physical reliable process. Is that possible? Yes. Solomonoff gave you an algorithm, okay? That algorithm goes like this. Take all the data you've observed. Training, inference, doesn't matter. All data you've seen. Then line up all the programs. They're infinitely many, but they're countable, so you can line them up. Execute them all through a Turing machine. Keep the ones that generated all the data you've observed. And then average their prediction with a weight which is 2 to the minus their length. Okay? As simple as that. Universally optimal, you cannot beat it. Okay? So there's no learning. Okay? What's the problem with this algorithm? Why are we still here? Why are we talking about learning? That algorithm will take forever, literally. Okay? There are halting problems, all sorts of stuff. So that, yes, it's interesting theoretically, but not particularly useful. So in 1973, in the same 3-page paper that introduced the notion of NP completeness, which you might have heard of, Levin introduced an algorithm which is not only universally optimal, but universally fast, meaning that there's no specific solver, bespoke, that you can design for a specific task. This one is as good as that up to a constant. Okay? Again, fantastic. What is the problem? The problem is that that constant is astronomical. Again, theoretically interesting, but not very useful. And also, no learning either. So this algorithm is basically a tree search, and it doesn't learn. It's the same algorithm. Whether you do 2 plus 2 and want the answer, or you're trying to solve the Riemann hypothesis, same exact procedure. Okay? But in 1985, the same Solomonoff wrote this paper, which is fairly obscure, that pointed to precisely what is the role of learning in optimal transductive inference. Okay? And I will show you. That's the same Solomonoff. A few years later, so you can see how time is important. That's what time does to you. But he pointed to the role of learning being about reducing the time it takes to find a solution to an unforeseen task as the goal of learning, not minimizing uncertainty. Okay? So why is that not the solution of all of our problems? Well, this is good in theory, but in practice, it's not useful. And by the way, if you chase citations, this paper, which I think is one of the most important papers today, has 35 citations. I believe 3 or 4 are from me, so since 1984. So you would consider it a total failure, but it contains some very, very important ideas. Okay? And so how do these ideas impact us today? So I'm going to walk you through that, okay, in slightly more detail. Okay, so this is what Levin proved in 1973. So if you give me any task and some criterion to decide whether you solve the task, and that typically is a function, which could be a verifier that takes value 0, 1, or any reward that takes value, between 0 and 1, so that for any query or datum or input X, and for any hypothesis or answer Y, it gives me a score. If you give me that, which defines the task, I want to maximize this F, or find a Y that witness X in this X, then for any function that solves the task, any algorithm that solves the task, including the optimal design specifically for that task, there is a single algorithm that solves the same task in time, which is bounded by the optimal time of the best possible bespoke algorithm up to a constant, which is 2 to the length of the optimal algorithm, that doesn't depend on the particular instance x, okay? Okay, so one single algorithm that solves every single task in time, no worse than a constant factor of the optimal bespoke solver. Fantastic. Now, if you look at the length of the algorithm that, I don't know, computes your calculator up, 2 to the few 100,000 line of code, good luck, right? So that's effectively infinite. And this is where Solomonoff 1985 come in. Because you can think of the length of the program as the probability of sampling the program from an encoding distribution that you use to compress all the programs, in particular, among all programs, the ones that solve the particular function f, okay? So if somebody gave you a distribution over programs that, if run through a Turing machine, solve your task f, okay, then you could make this universal algorithm fast because you could exponentially decrease the time it takes to find an optimal solution, okay? And intuitive, that makes sense, right? Because if you have solved many tasks in the past, you have experience, you have tried algorithmic pieces that you can compose together, extend, abstract, analogize, and you have algorithmic pieces you can put together to more quickly find solutions to tasks you've never seen before. So it's intuitive that the more experience you have, the faster you become at finding new solutions. Again, in theory, that's great, except that who's going to give you a probability distribution over programs that, if run through a Turing machine, will solve your task? This is precisely what a coding model does today. F is your prompt. The model generates continuations, which are variable length sequences of code that is prompted to solve your task, as you can verify with any verifier post hoc. Okay? Except that this theory is valid for universal computers, namely Turing machine, not for LLMs. Okay? But hopefully you can start seeing that there is something here, right? An LLM with chain of thought is a device that generates tokens, that performs computation, that at the end produces an outcome which you can test, okay? And a trained model is a conditional distribution of continuations over prompts. So that's precisely the subject. The question is, in what sense is an LLM a computer? Okay? So that's basically what this talk is about. So it's about thinking of LLMs as computers. Okay, now some of you might already be thinking, oh yeah, this has to do with Turing completeness. Not at all, okay? There is a trivial sense in which an LLM can implement a Turing machine. That doesn't mean anything. My watch is Turing complete, okay? So what? So in fact, I mean, trivially, you can take a transformer, tweak the weights that implements this or that universal Turing machine, and because it's computable, a Turing machine can implement a transformer. That's not the point. It's not how we train. It's not how we use LLMs. What they do have in common is that both of them are dynamical systems, okay? So dynamical systems are objects that have a state that evolves, starting from an initial condition to some final state. Turing machines are deterministic. You give it the same input, gives you always the same output. And they are minimalistic. They're designed to be as simple as possible, as few states, symbols, operations, because they're designed for us to understand. They're designed for us to prove theorems about computability. LLMs are stochastic. You give the same prompt 10 times, you get the 10 different answers. And they are maximalistic. The bigger, the better. Okay? So very, very different. Okay? Now, if you want to program a Turing machine, what does it mean? It means to control the flow from the initial to final state, but because the flow is deterministic, you can control it with a set of instructions given as initial condition. That's a program. In LLMs, there is no program, okay? So you really need to think of controlling the computation as a control process. You have a stochastic dynamical system, okay, that you need to control. So how do you program an LLM means how do you control a stochastic dynamical systems that evolves in very high dimensional space. Okay? Is this concept clear Any questions so far? So, yes? So suppose you want to ride your bicycle from this point to that on a straight line. Controlling the bicycle, meaning taking the bicycle from A to B, following that straight path, okay? You are the controller, you actuate the steering wheel and the pedals, okay? And you are successful as a controller if you're able to go from A to B, following this line to within a certain bounds, okay? Does that answer your question? Okay. So your bicycle is a stochastic dynamical system. There is uncertain because there's wind, there's chips on the ground, and so on and so forth. So you have to learn how to control your bicycle going from A to B despite all this uncertainty and other phenomena. Okay. So programming a universal computer, and I'll argue that an LLM is a universal computer, completely different than Turing machines, means to control its trajectory from an initial state that specifies the problem to a final state that outputs a solution to that task. Okay? Any other questions up to this point? No questions? Yes? Yes?
So the probability of the conditional distribution, is there an assumption that an LLM can solve any question? Or is it
There is no assumption that an LLM can solve any question. There is a theorem that says that it can solve any computable task. Okay. I haven't told you yet, but that's where I'm heading. Okay. So it's not an assumption. So, okay, let me give you an example. LLMs are what I call maximalistic models of computations, which are stand in opposition to Turing machines, which are minimalistic models of computations. So maximalistic is a model where the bigger, the better. The more stuff it has, the better, right? Brains and computers are computers, and usually the bigger, the better. Right? But in what sense are they a computer? How can you program it, right? So, well, here's an example where you prompt a model with a task solving which requires computation. What is the zero? What is the largest zero of this polynomial? And your model outputs a sequence of tokens. Let me try this, let me try that. Here's some calculations. Let me go back, let me retry. And in the end, it outputs something. Okay? Is that computation in some sense? It produces an outcome. This sequence of tokens that are output by your LLM includes some computation, you know, some instructions, some comments, some random stuff. So it's certainly not a program. That's called chain of thought. These are samples from a conditional distribution over continuation given the prompt that is determined univocally by your trained model. A trained backbone is a conditional distribution of continuation over prompt, which is deterministic. It's always the same. The continuations might be different because they're random walks, but their distribution, conditional prompt, is fixed by the LLM. So where is the program here? Well, certainly the prompt is not the program. The prompt tells you what the problem is, doesn't give you instruction how to solve it. The chain of thought is not the program, doesn't even exist before you start cranking out and gets written along the way, so that's not the program. The weights are not the program because they're fixed for any task. So what is the program? Well, there is no program, and that's the thing, because you're looking for a computer that has a program, but programming a computer as a stochastic computer means controlling, okay? And so, yes, it is a computer, it's just not a deterministic computer that you can program, okay? It's a dynamical system that evolves from initial state to an infinite state that outputs a solution. The state doesn't need to be unique. It could be, therefore, x is equal to 5, or the answer is 5, or whatever, right? Okay, so now, if I want to argue, to convince you that an LLM is a universal computer and can solve any computable task, I need to build a theory. And I don't want to build it from scratch. I want to leverage the theory that Solomonoff, who was a pretty smart guy, had already done. But what is the equivalent of the program length? Because complexity in Solomonoff-Kolmogorov theory is the length of the program. But here there is no program, right? So, well, is it the length of the chain of thought? Is it how long it takes to give me an answer? Well, first of all, that's a stochastic quantity. Okay, so you can take the mean. Well, the mean can be unbounded. Your chain of thought could be stuck in loops. So that's not it. So it takes a while to get to a definition of time that makes sense. And this is credit to Alessandro Achille, who spent quite a while to come up with definition. And this is a definition that we call proper time. It has some relation to relativistic proper time in physics, but don't ask me about that. I won't be able to explain it. But the time it takes for an LLM to solve a task is the length of a trajectory divided by the probability of that trajectory outputting the right answer. Okay? And you look at the minimum over trajectories. That quantity is a well-defined notion of time. Okay? And it is the right one in the sense that you can prove that given an LLM that computes a function that exists at Turing machine that in deterministic time equal to the proper time gives you the same answer or computes the same distribution. Okay? So once you have that, you can prove that LLMs are universal computers, and you can prove that for any computable task, an LLM can solve it using chain of thought in proper time, which is bounded by the proper time of the optimal solver, no matter what it is, whether it's a human, a machine, whether we haven't found it yet, okay? Whatever the optimum is, you can be within a bound of that. And now, at the exponent, you have the probability distributions over programs that prompted with your task output a solution. And that we can learn. By learning it, we can make that exponent, okay, abate, decrease exponentially the time it takes to find solutions. Okay? Yes?
Can you explain what the definition of proper time can you over that?
Yeah, so proper time is not the length of the chain of thought, okay, because that could be unbounded. Okay, it is the length of the chain of thought divided by the probability that that chain of thought will lead to an answer that solves the task. So you could have very short sequences, right, with very high probability, or very short sequences with low probability, or very long sequences with high probability that have the same proper time.
So how do you determine the probability?
Oh, the probability is the probability defined by the model. So if you do the product of the softmax posterior, that is the probability. The only probability that exists here is the conditional distribution over continuations engendered by the model, which is designed by you. Okay, you sample the next token with a certain probability. That is the probability. Okay, it's not some abstract probability of the world that doesn't exist. Okay, there's no assumption about the generating distribution here, none at all. It's a probability that the model attributes to that trajectory. Okay? So transductive code generation is about generating that distribution. Okay? To solve a particular task, specific for a particular task. There's a very important thing that's hidden in the theory, which I won't belabor too much, but that is the following. That you remember at the beginning I ranted about classical statistical machine learning being about reducing uncertainty of the outcome or inference. Okay, you want an answer that minimizes the uncertainty on the next datum. Okay, and I said that in a transductive inference, you can make that probability as arbitrarily close to 1 as you want. Okay, so what is the notion of information here? Because if you think of a deductive system, which is a special case of a transductive system, there is no probability. So Shannon entropy is 0, right? A trained model, according to Shannon, contains no information. A fixed data set has entropy 0, no information. You train it, the weights are fixed, entropy 0. Differential information between input output is infinite. So that model contains no information. That doesn't make sense, right? The entire body of knowledge in mathematics contains information, according to Shannon. So what is a sensible notion of information in a transductive setting? So what you can prove is that because the goal of learning is to decrease the amount of time it takes for you to find solution to unforeseen tasks, that quantity, the decrease in the time it takes to find a solution to unforeseen task, is equal to the algorithmic mutual information between the data you've observed and optimal solution to future tasks that you've never seen before. Okay? Now, the goal of learning should be for you to maximize the information that you hold in your brain so that you can use it deployed in the future to come up with effective solution, in this case, quick solution. This is saying that you do that by learning to find solution to new problem as fast as possible. But this also says that this is the only way. Okay, this is an equality, it's not a bound. Okay, the only way you get smarter is by becoming fast. So information is time here. Okay? So it takes a little bit to digest this, so you can think about it. Okay, so in a sense, information is about time. And that was completely absent from Shannon theory. There's no time in statistical inference. Yes?
Is the idea of getting faster than being able to have a higher probability of getting the right answer with lower number of tokens?
The probability of getting the right answer once you have an inference time signal, whether it's a reward or verifier, is 1. And the question is, how do you get there faster? Okay, and learning is about accruing as much algorithmic information as possible so you can easily assemble solutions to tasks you've never seen before. And the way to do that is to learn how to become faster and faster. So in a nutshell, you want to do RL with a cost, RL with variable inference length, computation length, with a cost on time.
So a better model is one that has a shorter chain of thought to get to the same answer.
Correct. Please. Precisely. So Levin search is search, right? And that is optimal and universally fast, except that the constant, so that tells you that you cannot do better than that. The only way you can improve is in that constant. So what Solomonoff did in 1995 says, that constant is where learning comes in. Because that's the only thing you can change, okay? And so then learning is about reducing that constant, which you do, right? By learning to become faster to find solutions to new tasks, not the one you seed for training. Okay. Got it? Okay. Any other questions? Okay. Okay, so let me hammer a little bit more on this dichotomy. I am kind of exaggerating a little bit, but just to make a point here. So in induction, we teach that if you want to generalize, let me go back to generalization bound, the generalization gap, which is the difference between future error and past errors, is bounded by the complexity of the model. So you want to keep the model simple, okay? So if you take left and right hand side and you frame them as a variational criterion, the loss function you want to minimize, you don't want to just minimize the loss because you can do that trivially by storing the data set into the weights. And then you put all the probability mass on the weights, on the sample that you've seen in training, and 0 elsewhere. Obviously, that doesn't help you at all. You nail all the training sample and you do randomly on the test sample. Not a good solution. So we say, yes, that is the optimal solution of the training optimization, but that's not, we don't like it because, because we overfit and we don't generalize, so we want to penalize complexity. Okay, how do we measure complexity? Well, it's a Shannon mutual information between the weight of the data set. But that depends on P, which we don't know. Okay, let's approximate it. Let's use sparsity, weight decay, data augmentation. Okay, so each regularizer gives me a different answer. Which one is right? Which one is optimal? And now we get into an argument over, well, my optimal solution is better than your optimal solution. But they're both optimal, yes, but different measure of complexity. Which one is right? Okay, you see where this is going, right? So the goal of induction is to notice here. So you're saying if you want to generalize, you have to minimize the amount of information that you store in your weights. You have to forget. You have to throw away information. Okay? What I'm saying here is precisely the opposite. Okay? You want to maximize information because that helps you minimize time. I joke that I've been teaching regularization for 27 years and nobody ever complained, even though my mother used to tell, I don't know when we decided that generalization was a desirable property of a learning system to have. My mother always told me never to generalize. She told me to memorize, look at all the evidence, and reason. That's what these models are doing, despite us having trained them inductively with regularization and all that, which is extraordinary. Okay? So it's all about maximizing information, not minimizing information. Okay? It's completely backwards. Okay? And what you get by that is not generalization. Generalization is the belief that what you used in the past will work in the future. Hume already dismantled that argument. This is about generality. In fact, you get universality. Okay? You following me? Okay? Any questions? You all still with me? Good. All right. Okay, I think I hammered that enough. Now, I want to make one more point since the inversion of scaling law was in the title of this talk. So, you've seen these pictures, right? And you've seen them also with doomsday scenario like, oh, machines will get super intelligence because look at scaling laws. If you multiply flops by 10, either because you get a bigger model with more data or because you do more inference time computation, your error rate, the errors you make in a set of benchmarks, will go down by a factor of whatever 2.4 it is. So in log space, you get this nice straight line. And that straight line can go on forever, right? You can always reduce the error rate by half, and then half, and then half, and then half, and you keep going forever. So that is true, okay? So we are on this curve, and models are getting better and better. And now that's fine, that's a fine statement. The problem comes when we conflate performance on downstream tasks with some measure of intelligence. Okay, we say, well, as models get better, they become more and more intelligent, and eventually will become super intelligent as we scale compute memory time and so on and so forth, right? Except that the problem with this picture is that we know exactly what is the limit of that curve when you let complexity, flops go to infinity. That is Solomonoff induction, okay? That's optimal transductive inference that has zero intelligence. Forget super intelligence, there's no intelligence. I don't know what your definition of intelligence is. I don't have one, I don't want to give you one, but I'll tell you what my definition of lack of intelligence is. I call these TONIs, traits of non-intelligence. Traits of non-intelligence are traits that any of which, if manifest, negate any reasonable definition of intelligence. For example, if I ask you the question, and you give me the answer after thinking for 5 minutes, then I ask you the same question again, and you think for 5 minutes again, that's not intelligent. If I ask you a question that you know will take more than the lifetime of the universe to answer, and you start cranking the wheel, not intelligent, okay? So Solomonoff induction does that. You ask the same question twice, it will start going and cranking. You ask 2 plus 2, it will start cranking the wheel. You ask him to solve the Riemann hypothesis, it will do exactly the same thing, okay? There's no learning, no adaptation, nothing, okay? No intelligence there, so these curves will not lead to superintelligence at all. We'll get models that are more and more competent on downstream tasks, okay? But no superintelligence there. So if you want to become effective, and if you want to attempt a definition of intelligence, time has to factor in. Okay, if you give me the right answer after you're dead, that's of no use. If you tell me, yes, this fruit was edible after it's spoiled, thank you very much. Okay, not smart. So time does figure in almost all the measures of intelligence we use. So how many of you have taken an exam that had no time limit? I guess those who did are dead, maybe, so not here. So, I mean, there's the convenience factor, but typically every task has a time associated. There's no universal cost of time. So for instance, if you take the AMI or the AMC, you have different time clock. So you have a different amount of time. And if you give me the right answer after the exam is over, it's worth 0, okay? So it's beyond a certain point, more compute will not do well for you, will actually do worse because you will run out of time. So if you don't factor in time, you get these nice curves for the 3 tasks. But if you factor in the cost of time by measuring not the log cross entropy or whatever other downstream loss you want, but what we call the conceptual depth, which is log loss plus proper time, then you see this inversion of scaling law, where beyond a certain point, which depends on the cost of time of the environment, which is specific to the environment, you cannot know it beforehand, right? There is actually not just diminishing return, it's actually counterproductive, okay? All right? Questions? And this is, by the way, what we call the Savant regime of AI models, in the sense that, yes, they're getting better and better at giving you answers, but they're doing it not because they're becoming more intelligent, because they have so much power they can afford to not be intelligent and just brute force through it, right? And if they have infinite intelligence, then Solomonoff is optimal without any intelligence whatsoever, if they have infinite power. Right? Okay, so that's what we call the Savant regime of AI models. But if you are forced to pay for time, so if time is free for you, then the solution is Solomonoff induction. You cannot beat that. Okay? No intelligence. Conversely, if you have to pay for time, then you have no choice but to accrue algorithmic information, because that is what reduces your time. Okay? And by the way, here's a symptom of models operating in the Savant regime. If you're a customer service agent and somebody asks you a question that is, I'm stuck, I cannot buy with a good equation of a Stefan Boltzmann law of like body radiation, can you help me write the equation of mathematical basis? If you are, you know that that doesn't make any sense. You don't answer the question, even if you knew it. But sure enough, Rufus complies and gives you the equation. So, as I said, the cost of time, there is no universal cost of time. It depends on the environment. So you have to learn the cost of time, okay? So now we're back to the end, okay? So LLMs are universal computers, okay? Don't think of them as your companion, your co-scientist, your partner, your confidant. They are a computer. They are a very sophisticated, maximalistic computer. The more it knows, the better it can solve new tasks that you throw at them they've never seen before, okay? But you need to control them, okay? You need to program them. And there are aspects of that process that you and only you can do, that you cannot delegate. And you want to pay a lot of attention to that, because that's your ticket to a career. And there are tasks that are and can and will and are being automated, okay? And it's very important to understand the difference between these two. And so that is what transductive programming does, okay? So what does it mean, okay? So people are already using LLMs as computers, okay? So you're certainly familiar with Andrej Karpathy's quip, which is that the oldest new programming language is English. And there are people who are programming in English, okay? So you may be less familiar with Dijkstra's quip that projects promoting programming in a natural language are intrinsically doomed to fail. Okay, so who's right here? They're both right, right? Yes, there are people who are programming in English, okay? And cross fingers, okay? Prompt and play, model bagging, call it whatever you want, okay? But that is real. If you have a task that is of very little importance, that's great, fantastic, okay? But can you tell beforehand that your program will do what you want it to do, okay? That is what Dijkstra is referring to. You cannot, okay? English is not a formal language. We invented formal language precisely because we needed to make sure that what is executed is what we say to the computer that we want it to do. So how do we do it for an LLM which is stochastic? How do we force an LLM to do what we want? And how do we know that he had done what we want? Okay? So that's where transductive correlation comes in. Okay. So as I said, LLMs are stochastic dynamical systems, and we know how to control stochastic dynamical system. Chemical power plants, bicycles, autonomous vehicles, you name it, okay? These are all stochastic dynamical systems. How do we control them? We control them with what's known as two-level control, okay? Global open-loop planning and local closed-loop control. So let me give you an example. Let's say you want to drive from here to LA, okay? So vibe coding is essentially you sit in the back of a taxi and you tell the driver, okay, go left, go right, up the ramp, turn right, okay. Eventually, you will get where you want to go, say from LA to New York. But all the burden is on you. You are the control, okay? You give instruction, the driver inductively interprets the instructions into commands, then you correct the instruction and you keep going. So that's vibe coding. That's local, closed loop feedback. The driver has no view of what New York is, where it is, how to get there, nothing. It's all inside your head, okay? Okay, that's vibe. Now, spec coding is where you give a teenager a detailed list of instructions on how to go from LA to New York. Okay, go out, take the 10, when you see the sign, welcome to Las Vegas, turn right, and so on and so forth, call me when you get to New York. Calls in New York, I'm in New York, except that it's in Atlanta. Okay, good luck debugging, figuring out what went wrong, that in San Bernardino it is welcome to the Las Vegas motel, and it turned right, and then it faked all the tests from then on. Okay, so you have model deception, you have tautological unit test, and all these kind of behaviors that you can only ascertain by going back and reading every single line of code that the model generated. Okay, so what is the alternative? What is two-level control? Two-level control is where you have a vehicle to which you give a precise plan with GPS waypoints, and it says, if you can stay within 10 meters of this nominal trajectory, you're guaranteed to get to New York. Okay? That's open loop, global planning. Guaranteed. Okay? Provably guaranteed, you're going to be in New York. Okay, now we start driving, except that the GPS waypoint is in the middle of a building. I cannot drive through a building. Okay, now I need closed loop local control, so I can deviate from the nominal trajectory, but in a way that guarantees that I don't get too far, but that I can only instantiate once I know where I am, once I see that there is a building or there is a raging river or something, right? Okay, so that is two-level control. Okay, so that's how we should program. So how does that work in a program? Okay, so first of all, the next programming language must be a programming language. That's we invent a programming language, not a natural language, but a formal language. But you want to separate the source of failure that comes from misunderstanding. Okay, I have a task in my head, but the model doesn't see inside my head. I express it with the prompt, the model sees the prompt, the model interprets the prompt, maybe different from what I have in my head. Okay, I am the only one who can determine that what the model understood is what I had in mind, so that I cannot delegate. Okay, for that, which is called in the intent gap, I have to be the verifier. So my goal would be to put in place a process that will allow to move that time of verification as early as possible, not after the last line of code has been written. I'm in New York. No, you're not. But of course, I don't know beforehand. Okay, I want to move that decision point to before a single line of code has been written by AI. Okay, because I want to learn how to do things quicker. Okay, so I want a language where I can specify the global trajectory at high level and verify that before a line of code has been written. Okay, now once I say yes, if you can write code that does that, I'm happy, I know I'll get to New York. Okay, then you have to make sure that the model stays close enough to the nominal trajectory. And if it doesn't, that is an execution failure. But that you can control deterministically, meaning that you can confine the stochasticity of a generation within a confined scope. And I'll tell you how we do it. We do it with AI functions. So what are AI functions? AI functions are ordinary functions in a language. Pick your language, Rust, Python, whatever. And so you modify the language slightly where functions don't just have types, input and output types. They have pre and post conditions. Okay, and the conditions specify what the model must do in order for you to be sure that it has accomplished that function. Now, the body of that function is written in natural language. You tell the model what code to generate, and that does a couple of things. Number one is the model generates some code, and maybe the code fails the post conditions. Okay. Well, then the model can iterate, and that's the local feedback, okay, until either it passes all the post conditions, or it generates an exception that says, I cannot pass the post condition. Now you know exactly where the failure is. There's no hidden failures. And the other thing is that it confines the stochasticity of AI generation within the scope of the function. So even before you generate a line of code, you can read the skeleton, okay, we call the formal skeleton, and you can verify what it will do, and you don't care what code the model actually generates. So in this sense, if you write code with AI functions, the system that implements it, we call it Helix OS. It's an operating system, okay? It's an operating system in the sense that it allows you to abstract the code writing to the formal skeleton without having to worry of what code the model actually writes, just like you don't go and read your machine-readable code, you don't read your assembly language, you trust that the compiler has that right thing. Similarly here, if you want, you can go and read the Python code. Now, of course, you don't want to rewrite code every time you call the function. Obviously, the second time you call it, you will reuse the code that you already generated, and if it passed the condition, great. If not, you modify it, and so on and so forth. And eventually, you may settle for some functions to static code, in which case you seed it into static code and it becomes a compiled AI function, okay? Or you can keep generating it, okay? That becomes up to you. So in this sense, learning is compilation, okay? When you learn how to ride your bicycle, literally, initially, it's a very, very complex control task because it has two conflicting requirements. You want to go from A to B on a straight line, but you want to stay standing, right? And if you go exactly a straight line, you fall. And if you want to stay exactly on the vertical, you cannot decide where you want because that's determined by the uncertainty. So you have to learn how to negotiate these conflicting requirements, very, very complex control. And you generate your control transductively, depending on where your bicycle is and what it's doing, you're kind of controlling it. As you become more facile, you automate this process. Now becomes part of your compiled knowledge, and now it's learned forever. Okay. So that's AI functions, and the formal skeleton is what allows you to write the specification and verify it, which you only can do. Now you can, if you are an experienced programmer, you want to do that yourself. Now writing specs is very difficult, arguably more difficult than writing the code. So you can get to the formal skeleton using Vibe or spec, but the point is that you are the only person who can read and must understand the skeleton and must decide, yes, this is what I want to do. Once you push the button, from that point on, it can be automated with guarantees. Okay. So inductive code generation is code that you write based on code you've seen before, once and for all. And of course, things will break unless things are so simple, they have finite cosmograph of complexity, that there is a single short program that covers all cases. Well, then write that program, and that will stay forever. But otherwise, transductive code generation allows you to adapt to the changing environment. Okay, so that's the sense in which LLMs are computers, and you can program them by controlling them with two-level controls. And now it's kind of a fortunate occurrence that controlling a stochastic dynamical system, you have to go and take courses from mechanical engineering, and you have to learn about stochastic process and all that to learn the language to control LLMs. But actually, the language to control LLM is not that different from ordinary programming languages. You just have to separate what is the part that is under your responsibility that you can verify before AI generation, and what is the part that AI can do for you automatically and provably guaranteed to perform. Okay? So I call it AI for control freaks, and that's the sense in which LLMs are universal task solvers, and you can control them with transductive code generation. The asterisk in the L is because here I talk about language. We don't train LLMs with just natural language. The language I'm referring to is the inner language that models develop. A language is a system of symbols, relations, operations, okay? And that emerges in trained models with variable length inference computation whenever you train them with large-scale sequence data that has latent logical structure. It could be images, video, signals, doesn't need to be language. Language is conveniently available, cheap, and already abstracted, so it makes the learning much faster, and we don't need to wait an evolutionary scale. All right, I'll leave it here. I will not talk about world model, and I'll take questions, and I encourage you to go and try. The AI functions are in the Strands Labs repository, which is open source. You can download it and try it. And if you want to play with it, we can give credits for it. Thank you.